My name is Otwin Othmer. I'm since '84 professor at California State University, and I was hired to teach finite element methods. And 2 volumes are now published in India, and to order them is very simple via email, and you can call them. The method of finite elements is well known as the general procedure in structural analysis, dynamic analysis, and also heat transfer and many other topics in engineering called simulation. The easiest way to learn about the basic finite element numerical procedure is to have an animation, and this animation software is called FA-Beam, and it is one-to-one documented in the first chapters in this finite element methods 1, and there is also volume 2 for more advanced procedures, but it is all based on the basic numerical procedure. And to do a simple frame problem, this is not to do many general procedures in finite elements. It is only to learn the finite elements, and all frame and beam problems are exact solved with FA-Beam, and everyone can also install this FA-Beam software. It is free. I give a brief introduction. We start with the input, and that is the first thing. The first thing, if you want to have a simulation done, you have to input coordinates and boundary conditions and loadings and the connection between the nodes. These are elastic connections, and they are named elements. So we start with the input of the nodes. There is node 1, I say 0, and in Y also 0. Then I have a node 2, I say 200, and also Y is also 0. We show the nodes alone, and here 0 in Y. Then we go for node 3, and we say minus 100. So that is not in X. I made a mistake, easily done. In X direction, we go minus 100. I was right. Minus 100. And in, let's say again, in X direction also I was wrong, 100, 200. So X direction 200, but now in Y direction I go minus 100. And then I have a node 4, and this node 4 this node 4 is again 0 in X but in y direction, I say minus 100. So now we want to make sure that we see that. So we click OK, and we see the nodes. Here I should go a little bit down, but you see node 1, and this is node 2, node 3, and node 4. Now we go again for we have the nodes located, and now we have to connect them by elements, and the cross-section is given here, and then there's a moment of inertia, then there's a Young's modulus, and there is a shear modulus. So we give values, we connect node 1 with node 2, and these are the values. Then we connect node 2 with node 3, and then we connect node 3 with node 4, and then we connect node 1 with node 4. And what you see then is a frame, and this is then named the elements, the beam element here, and element 2, element 3, and element 4. And if you make a mistake, and here is warning, state instability, yeah, we have to have now boundary conditions. This frame can move anywhere. And now I put in boundary condition back to input, and I say node 3 and node 4 are fixed, but the moments are free. So the translation in x and y are fixed, but otherwise the structure can move. So to show this, we see here, this is simply supported, named simply supported. So the whole structure can rotate here, but cannot move, and therefore cannot move here. So the warning is gone. We have now this fixed supported. The next step is we need a loading. So we go back and say only we have all possibilities, line loads and also moments, but we say only in x direction here a single force, and we put in here plus 100. And what we see then, we have here is a load. The file is there, but it is here not shown. But if I go and say now all steps at once, so I click here, and we see that I have done this load, not at node 1, but you see that is the difference of the frame. So I want to correct it. I can go back and say we did it at node 2 and not at node 1. So I get here rid of that. This is 0. And I put it at node 1. So this is here node 1. And you see then here 100, node 1. Now let's go again. Now you see this little arrow here. And because this is E1, is the beam is nearly rigid, if I go all steps at once, then it deforms this way. And you see it is here 90 degrees, but the joint 3 cannot move, but it can rotate, and that is all the members are rotating. And now I go through the whole procedure. So we have the input with no input of nodes, boundary conditions, and you are totally flexible to change it anytime. Then you have the stiffness of the 4 members, and so this is the exact deformation. And later at the end, we see exactly the deformation for each member. So now I go the procedure. These are the steps in finite element. Generation of the element stiffness matrices. I click here. We start this in the book. Is explained why for one-dimensional elements with shear deformation included, we generate in the book this stiffness matrix. And now we say, okay, these are the 4 stiffness matrices. They are connected, rigidly connected at the nodes. And now we do step 2. Now we see also the undeformed structure and the deformed structure, what we saw before. And now we go for transformation of the element stiffness matrices and forces, force vectors, to global coordinates. This is the animation. How we do it, here the transformation in detail, there is a transformation matrix. So that is in every detail explained. So now we go for every element, we go through the transformation from, it has to do where the members are located, and therefore displacements here are for visualization are larger than in reality. And so that is, we see here the deformation, but later we see the exact deformations. So the transformation is done of the 4 stiffness matrix. Now we have to assemble them. The assembling is this. We have in the global stiffness matrix the 4 stiffness matrices of the beams to assemble, and that's the procedure happening internally. Partitioning, and then it's all explained in detail in the volume 1. So we have assembled. Now reduce the linear system of equations of the whole structure due to special boundary conditions. So we click that, and we see here there are node 1 and 2, the global stiffness matrix after assembling, and these are here now after the boundary conditions are in, because there is no stiffness for node 3 and node 3, but only the translation is 0, not the rotation, and we saw it when we look at the graph. And so that is here. Now we next we go and see the reducing the equations due to the special boundary conditions. Now we do the solution, and here we see very important, the condition number is small, each power 4, so the linear system of equation is stable. And we go for the solution, and you find here the solution. These are the exact, here, translation X, translation Y, and rotation for node 1, and so on. And here we see 0 here. Node 3 has no translation but rotation. And here, so and then now we go and say the next step was here. We have done this. Now, back substitution of the known displacements to global coordinates to compute the unknown reactions in global coordinates. So if we click that, then we see that we have here the reactions. At the boundary conditions, there are reactions, and these are the exact, for the given loading, the exact reactions. And we do the next step. And translation of the known displacements, these we had calculated in global coordinates to special coordinate local element coordinates. And that procedure is the reverse from the beginning. And here is a transformation shown for all. So, and now we go the last step, back substitution of the displacement in local coordinates and compute the unknown forces and moments. This is here done for every the transformation explained. And now this is important for member one. You click now, for each member, you see that is the translation in, I say, at the end. And therefore I send 200 as we go in. At 200, we see here, that is here at 200, and there is a little dot. It has to be a little dot. There, that's the little dot. And at that point, we have a very small, if I say here, I go with 0, so at node 1, and then you see practically, because the member 1 is in axial direction nearly not elastic, and therefore it's nearly the same. And these are then Hx is the axial. I go also maybe at half the way at 100. So it's always exact. And there is the dot. You should see there, that is the line here. The dot is also constant due to the load nearly constant. And then third, I go in the here for Wx, and I go 400. And that is then here the exact solution, that's the green one. And the green one has also a dot. It is, here is the dot. And this is here the deformation of member 1 here, what you see, but this is the deformation. And here is also, let's go for 200 or 75. 75, no, 100, yeah, okay. 150, and we see the angle of the elastic line has an angle, and that is here 150, there is the dot. That is the angle here due to this elastic line. And then we can also have the moment, let's say the moment we want here in 100, and we find at 100 we have that 200, I said here, the moment, the moment, is here, the moment is here. And now the final step, let's say 450, 50, so we see here the for member 1, there is here the dot, and this was the dot for our axial force. And here is 150. We had here the rotation angle was this here. And here we have at the same location, here we have that is the, it has to be the, yeah, that has to be the shear. The shear deformation is here and also constant because we have only single loads. So you see the graph here, and at every location it is the exact value. You can calculate, and many textbooks calculate it, and to get first these exact values takes a long time. For that we have computers, and that you have immediately the graph. You can have hinges, you can have members rigid, and but that is for the first time. For other elements, we can go next element, and that's all. Then it is the same situation. For every element you get it. It's that is here element 2, and so on. So we go back to the beginning and just say a few words when we go to the input. So you can have for every element a hinge. That means the moment is here. The moment is free. And we can also have here the hinge for every element, and also we can have it elastic, or we can have it member rigid. So in hand calculation, this will be a long time. Therefore, in the book, these examples are calculated, and with a FA beam, you can immediately have results, and these are exact results. I think you cannot find anywhere a software which is showing via animations, like I demonstrated, the process how the finite element method numerical procedure is performed. Thank you very much.